So I need you to take a few notes, basically get some definitions down to prepare you for our next lesson, which will be like dissolves like. Remember to write down things that are in yellow. So to start out, are the molecules below polar or nonpolar? Pause the video here so you have time to think about it. Write these things down and give it some thought. What do you think, polar or nonpolar? So hopefully based on all the things that you've learned so far, you now know water is polar, and this hydrocarbon, where it has only carbon and hydrogen, no other bonds, is nonpolar. All the bonds in that are nonpolar. So if I were to tell you that the C16H34 is oil, do you think it's going to mix with water? Based on your background knowledge outside of school, what do you think? Oil and water, are they going to mix? And maybe looking at this slide, you have some idea of why that's the case. So the objective is to use intermolecular forces to predict solubility and miscibility. Let's define those two. Solubility. Solubility is a solid dissolving in a liquid. Now it can also mean a gas dissolving in a liquid. That's a more unusual case. Right now we're really interested in solving solids dissolving in liquid. That's what we care about. So for example, salt dissolving in water. Miscibility means two liquids mixing together. So an example of miscibility, if you mixed water and milk, you can get those two things to mix together. If we look at the opposite of soluble, what's the word that means opposite of soluble? Insoluble. And opposite of miscible? Immiscible. Two M's in a row there. Okay, so immiscible. You should be able to easily think of two liquids that are immiscible, two liquids that will not mix together. We just mentioned them a minute ago. All right, rule of thumb for solubility and miscibility. Our rule of thumb is like dissolves like. So I don't know if you've heard of a rule of thumb or not. Hopefully you have. A rule of thumb is a general guideline. It is something that is most of the time true. It's not a law. It's not set in stone. There are exceptions, but it's generally true. It comes from the phrase rule of thumb comes from the idea that the king, the end of his thumb, like the last joint of his thumb, was considered the length of 1 inch. So when you got a new king, you've got a new inch, a new unit of measure. So rule of thumb, his thumb was the ruler. Okay, so it's a general guideline. It didn't mean that an inch was the same length all the time. It was just a guideline. You get a new king, you get a new inch. So like dissolves like is a guideline. It's generally true most of the time. Sure, there are exceptions, but it will guide our thinking and help us out most of the time. So let's see what like dissolves like actually means. It means polar mixes with polar. If you have two polar molecules, they will mix together. They are alike, so they mix. Nonpolar mixes with nonpolar. They are alike, so they will dissolve into each other. Nonpolar with nonpolar. So what do you think ionic mixes with? If you have an ion, which one is it more like? Do you think the ion is more like a polar molecule or a nonpolar molecule? So hopefully you realize that an ion is more like a polar molecule. So ionic compounds mix with polar. Polar is partially charged, and ion is completely charged. Nonpolar is not charged. So the ion is more like a polar molecule than a nonpolar molecule. Like dissolves like is going to tell us ionic mixes with polar. Now, at this point, some people ask me, well, why doesn't ionic just mix with ionic? It does. That is true. That does happen. It's just not a very practical application, because what we're saying is we have to have a liquid ionic compound in order to have a solid ionic compound dissolve into a liquid ionic compound. But ionic compounds have extremely high melting points. We saw this in lab. We've talked about this. To melt table salt, for example, is like 800 degrees C. So very seldom do we bother. There aren't very many practical applications where we melt an ionic compound to create a liquid out of it. It just doesn't come up. So if you did it, yes, it's true. An ionic solid would definitely dissolve into an ionic liquid. But since we will never deal with an ionic liquid in this classroom or in everyday life, what we care about is that an ionic solid will dissolve with a polar liquid. So the explanation of why it's true, polar molecules are very attracted to themselves, strong intermolecular forces. We've seen this. So you have to pull those molecules apart to allow other molecules to mix in there. You're going to have to overcome the intermolecular force, separate the molecule, and then something else can come in between. Only an ion or another polar molecule is going to be able to do that. Only something that is already charged is going to be able to push its way in, overcome those forces of attraction, because it itself is also attracted. They're all attracted. So that's why ions and polar molecules can mix into other polar molecules. But a nonpolar molecule has no way of getting in there. It has no attraction to the polar molecule. It has no way of separating two polar molecules to mix in. Nonpolar molecules are not strongly attracted to themselves. We know there are dispersion forces, but we know that those forces are weaker than a dipole-dipole interaction, for example, or hydrogen bonding. So the nonpolar molecules, they aren't trying to keep other molecules out. Other nonpolar molecules can easily move in between them. There's just not a strong force of attraction holding things together. The polar molecules have no interest in moving into nonpolar molecules. Polar molecules are attracted to themselves. They aren't going to separate to go mix in with something that's not charged, that doesn't have a partial charge to it. There's no attraction between the polar and the nonpolar that's strong enough to overcome the attraction between polar and polar. So these are the reasons why we see like dissolves like, why polar mixes with polar, nonpolar mixes with nonpolar, and ionic mixes with polar. That's the end of the slides today, and we will use this information in class tomorrow to analyze some molecules.